right? So this slide basically shows that what are the difference between states of a physical machine and a virtual machine. So state means what are the different steps in their life cycle. So if you see on the left hand side, green, a physical machine has 3 states: on, off, or paused. For example, for your laptop you can do shut it on, power it on, shut it off, or you can even pause your machine, maybe make it sleep. But if you look at on the virtual machine side, as compared to the physical machine, you can do many more operations, such as you can save a running virtual machine. For example, if you look into your Docker coursework, you can use this copy command, or even call save command to save the state of your Docker container. You can pause your virtual machine. You can go from defined state to undefined state. So what basically this shows that as compared to physical machine, we have many more operations in context of virtual machine. Why you think in this picture we have this state of defined and undefined? What could be a state of defined and undefined in context of virtual machine? Anything else? What would be defined and undefined? So if we say a virtual machine, right? A virtual machine, if it just has based on operating system, but it doesn't have any application logic. So you can say the main function of that virtual machine is not defined. It just gives you an environment where you can run your application, like web server, DB server, load balancer, whatever. When it becomes defined, when you actually give it a role, what is this virtual machine supposed to do? Define also means that, so you can have, say, one Docker image that can be sitting on your laptop in a state which is undefined, in the sense that it is not decided where it's going to run. It's run on your laptop, it's going to run in Amazon cloud, it's going to run on Azure cloud. It is not defined what kind of application logic going to run into that. So that's why if it's sitting as a file, it's called as a undefined. If sitting as an image, when its role, its context, its deployment scenario is not decided, it's called as undefined state. But when you add the context to it, that okay, this image is going to run on certain hardware in certain data center with this application logic, states change to defined, because now you have defined a role for that virtual machine. And when you do the coursework, you will understand that you can do many operations with your virtual machine or the container, including saving, restoring, suspending, resuming. Even Docker gives you interface to migrate your running container instance from one host to another host. So that was one of the most powerful feature of virtualization, that being able to migrate your running application instance. And of course, as compared to this hypervisor-based virtualization, that is much simpler and easier to do in context of containers. Why is that? We will cover that when we actually go in details of how a Docker container engine is organized in terms of operating system dependencies and application libraries. Right, so this picture again shows that, okay, you have a hardware. On that hardware, you have hypervisors. On that hypervisor, you can create multiple virtual cloud machine or virtual machine that can convert your CPU to virtual CPU, your memory to virtual memory, your disk to virtual disk, your network to virtual network. And all this conversion from CPU to virtual CPU to virtual memory is all done by a software called hypervisor layer or the virtualization. In some literature, it is also called as virtual machine monitor. So to simplify your understanding, a hypervisor is the operating systems of operating system. Why I'm saying that? Because our virtualization is managing many operating systems inside a virtual machine. So in the old days, when we didn't have virtualization, one operating system used to manage the hardware, as we see in the initial example. But with virtualization, you're adding one more layer that can manage many operating systems. That's why a hypervisor is called as the operating system of operating systems. Right. So in this picture, you see two competing approaches. I mean, one old approach, one new approach. On the left-hand side, you see a non-virtualized operating system that I just said a few seconds ago. So in this picture, the hardware is not virtualized, it's managed by one operating system, and the operating system is controlling all this virtual CPU, all the CPU, network, memory. While in the other picture, you add the virtualization layer, and then the operating system layer moves up the scale that goes inside the virtual machine, and now the hypervisor layer is managing the up layer operating system and lower layer hardware. So this is how non-virtualized and virtualized system differs from each other. So instead of all the hardware being managed by a single operating system, your hardware is managed by a hypervisor, and then in turn on that hypervisor you can run multiple operating system. Like you can run on the same hardware Ubuntu OS, or you can run Windows, you can run Mac, as many you want, because they all are now going to talk to the virtualization layer. Right. So now going more in detail of how to understand the role, to understand the difference of role between physical hardware resources, the virtualization layer, and the virtual machine. So at the bottom layer, you have the physical hardware resources that offers you this memory, disk drives, networks, and servers. And now, on top of that, instead of running operating system, you run this virtualization layer or virtualization interface, whose main function is to create multiple copies of virtual resources and somehow map them into the physical resources. How to create a virtual CPU and create allocation for that on the physical resource. The second goal of virtualization layer is how do we isolate resource allocation between different virtual machines running on the same host. So as you see in this picture, you have you have this fixed set of hardware on which you're running a hypervisor, but on that you can, as I said, you see in the previous example, you can create multiple virtual machines, and then if you match the color, those blue ones running on the blue ones on multi-core computer, the virtual hypervisor needs some mechanism to be able to, at the runtime, map and distribute this physical hardware resources across those virtual machines. And how this distribution and multiplexing resources happen with the virtual machine depends on what kind of hypervisor it is and what kind of virtualization technique it implements. So either it's type 1 hypervisor or it's type 2 hypervisor. That's first level. And then either this type 1 or type 2 hypervisor either implements full virtualization or para virtualization or hardware assisted virtualization. So we'll look more into that. So of course, at abstract level, its job is to create virtual resources and map them to physical resources, but how actually it's implemented inside the hardware software actually depends on either this type 1 or type 2, and what is the mechanism of virtualization, either the full virtualization or para virtualization or hardware assisted virtualization, or it could even be based on Docker, which is called container-based virtualization. So we have end with these 4 different ways to virtualize your cloud data center and application, and depends on which of the virtualization approach you use, you will have different performance and security footprint on your application, which is very important to understand when you want to deploy application in the cloud. So the first part of is this kind of virtualization based on hypervisor leads to something called server virtualization, which is division of a physical system resource, processors, memory, I/O, where each set of resource operates in an independent way and can be shared across application. So why you think this server virtualization is always looked different than network virtualization? Remember our factory topology, that was the network. And now I'm not talking about that. So why you think the server virtualization techniques cannot be used to virtualize the network as well? Because key to cloud computing is not to just virtualize the servers, but we also need to virtualize the network. So why can't we use the same hypervisor layer to virtualize both data center network as well as data center servers? What could be a reason for that? Why we need to see these two in two different perspectives. So one dimension is server virtualization, and then other dimension is network virtualization. What could be the distinctive features, distinctive requirements? So to understand that, you have to think what you do on a computing server as compared to what do you on the network. The question is, why can't we use the same server virtualization hypervisor software to virtualize both servers as well as underlying data center network, which is based on, say, our fat tree topology, that is aggregation layer, core layer, and the access layer? Why go this extra mile to create this different pieces of software to virtualize network and virtualize servers? Yeah.
Because the network works where BSPs handle physical network failure.
Yeah. So the functions to be done, the translation to be done on the network layer are different for what you do pretty much on the servers. So what actually we do on the network? We share the bandwidth, share the different traffics from different servers. They share the same network media, and you need certain way to isolate the traffic in a way that that you can create multiple kinds of network on the same network hardware. So the short answer to that is the type of operations that we do on the network is fundamentally different on type of operation that we do on the physical hardware. Here we execute machine instructions. So we need to virtualize those machine instructions, but on the network we actually send packets. So we need some way to virtualize the traffic. So there are two different parts of your computing paradigm. So we cannot use the same hypervisor to virtualize both network as well as the server. That's why we will first study about server virtualization, then we move into how to do network function virtualization, that is called NFV, using software-defined networking. So that we need to see both of these things in isolation, and then understand how virtualization differs across these two different computing paradigms. So going back to this discussion, so virtualization in the cloud is the key enabling technology of cloud computing that allow pooling of heterogeneous computing resources. So it's because of the virtualization we are able to consolidate multiple applications, each with its own operating system, on the same set of hardware or same set of data center rack. And there are two types of virtualization which is used in cloud computing. They include server virtualization that we discussed, and next is network function virtualization. We'll have different lecture on that. So you all of you are working on Docker. So you think Docker is server virtualization, or it's even higher than that? Can we call it application virtualization? This Docker containers. So this is one more layer. Of course, we can abstract as server virtualization, but actually what you're doing is you're virtualizing your application components, because your Docker engine is dependent on the operating system underlying. So it's more than server virtualization, it is application virtualization. Then how do we decouple the Docker from the operating system if we have to as a cloud provider? I already told you guys, maybe I'm asking other people, how do we decouple the Docker from the operating system layer, which was the always goal of virtualization. We don't want to be stuck with one operating system. So how do we do that? Thinking what you're doing in your coursework. Because the Docker, we again end up with the same situation. We are stuck with that operating system where Docker engine is running. And we want to break that paradigm that was the original goal of cloud computing. To run Docker inside a virtual machine. That's what we give, right? Virtual box. That's what it said. So that's the way to run Docker itself inside a virtual machine. Then the server virtualization is actually done by the virtual machine and you're running inside that. But what could be the problem with that? So now you're using two-layer virtualization. One is server virtualization through virtual machine, and then you have application virtualization. Performance. You get a performance hit because you have this multi-layer virtualization, but then it also simplifies in the sense that you're not stuck with one operating system where that Docker engine is supposed to run. So virtualizing processor, disk, and memory is classified as server virtualization, and then virtualizing the data center network using software-defined networking and network function virtualization paradigm is called network virtualization, and we will have 1 hour lecture on that after we finish this one. Right, now let's go into detail on how to create hypervisors and what are the different types of hypervisor available. So if you see in this picture, what are the major difference between type 1 and type 2 hypervisors? Yeah, let's give someone else a chance as well. So what's the major difference between type 1 and type 2 hypervisors? Host operating system, right? So if you see in the type 1, it doesn't show any operating system. Will that be true that you have a computing system without operating system? So type 1 hypervisor, they run on the hardware directly and control and monitor the guest operating system which is in the virtual machine, but there is no operating system. So how this could have been implemented? Can we have a computing system without a hypervisor? I mean, without operating system, this is what it's showing. So what it means? It means that operating system logic is that code base is implemented as part of the hypervisor. On the other hand, if you do the type 2 hypervisors, it runs over a host OS, so the host needs to be maintained, the server needs to have a host OS. On top of that, a type 2 hypervisor runs, and on top of that, different guest operating systems are running. So out of this, which you think will be the faster one? So in terms of running an application, which you think will be faster in terms of executing your instructions? Of course, to go real answer, you need to do benchmarking, but beyond that, even from your top of your head, given the layers in the environment, it seems like type 1 will be faster because you don't have this extra layer of operating system. But then again, the term faster is quantitative, so only way to verify is to benchmark your application on the 2 different type 1, type 2 environment, and then check from there which could be faster. But in terms of the hierarchy, it seems like type 1 will be faster than type 2 because you don't have this extra layer. For example, you have to first translate from the guest OS to the host OS, and host OS needs to translate to the hardware. So you have multiple level translation, so that is not there in the type 1, so it seems faster. But then again, it depends on what workload you're running, what is the hardware configuration in underlying data center. It depends a lot of things, so that you can only actually determine by doing the benchmarking experiments. It's not so straightforward just knowing type 1 is faster than type 2. Right. Okay, so we are using a type 1 hypervisor with no operating system, and this picture shows how your instructions from your virtual machine is executed on the underlying hardware. So what happens in the implementation of operating system, that we have different levels of access privileges. So if you know about kernels, operating system kernel, this is the main core operating system, they always run on ring 0. So ring 0 means it has the highest level of privilege over the hardware. So what happens in the type 1 hypervisor is all the application they run in either ring 1 or ring 2, they set out certain instructions which goes to the guest operating systems, which thinks that it is in ring 0. So what happens in this one, that guest operating system is not aware that it is being virtualized. So it thinks I am in the most privileged mode, and it's trying to execute the instruction, and pretty much instruction is not executed because it raises a trap on the type 1 hypervisor. So based on this picture, you can view hypervisor as a gatekeeper to the operating system. So all the operating systems running on top of this hypervisor sends this privileged instructions in the kernel mode that they need to execute on the hardware, but they are not able to execute. So what a hypervisor has to do is they have to catch those instructions as they interrupt or traps, and then based on what kind of resources is requesting, like memory or CPU network, it has to then translate that to the underlying hardware. So although the operating system thinks that it's the real kernel which is running the whole system, but in theory it's not the real kernel, it's the hypervisor is the real kernel, and then the hardware, the hypervisor and operating system, they communicate through something called the instruction track. It's like something similar to this. So like you have a hardware, and there's one way to enter the hardware, which is through this door, right? And you have hypervisor sitting at this door, and it's its job to coordinate the entry into the hardware. And how it works is like this. So you have multiple virtual machines running on top of this hardware, and each of them somehow believes that it has full access to the door, full access to the hardware, but in reality it doesn't have the full access. What it actually is doing is it is knocking on the virtual door. And by knocking on the virtual door, it is raising something called software interrupts or traps, which is a terminology in computer architecture that if you want to do something on the hardware, it is not done, it just raises an exception in the hypervisor, and through that exception, the hypervisor got to decide which of this virtual machine has the priority to go in first. So that brings us back to the pricing policy of cloud computing. So if you go to Amazon Web Services, you will have virtual machine with different prices. Some will cost you £10 per hour, some will cost you £5 per hour, some are even free. But how does they come up with this pricing policy? They come up with pricing policy based on how much privilege they have to enter this door. So if this was £10 per hour, it will have the maximum privilege to enter this door. So if there's an interrupt coming from that VM, the hypervisor will give us the best preference to you go first. So that's why if someone wants good performance from this public cloud provider, they always have to check its price, because based on that price, you get more privilege on the hardware. So that's where you have to weigh the pricing and the performance thing, because that actually determines how easily can you get access to the hardware. So this kind of pricing logic is implemented by Amazon inside the hypervisor. Based on what kind of virtual machine template you purchase from them, it gives you different priority to your request. So this is the reason why I call it the operating system. So operating system, because this kind of instruction management is done by each of those operating system as well. But now what this hypervisor has to do, it has to become a super operating system that has to manage the instruction translation from each of the operating system running in different virtual machine on top of that. Okay, so this kind of coordination between the operating system to the hardware by the hypervisor can be done in 3 different ways, and they are called as full virtualization, para virtualization, and hardware assisted virtualization. So this type 1 and type 2 hypervisor could be implemented based on any of these techniques. So like company like VMware, they support all three virtualization techniques. Based on what you need, you got to decide. So looking at this picture, what do you think is the difference between full virtualization and para virtualization? So this is a VM with operating system, and so each VM has operating system. So what the distinctive feature is that, so in the para virtualization, you see that the VM has a yellow color. That basically means you are modifying the code inside the operating system of the virtual machine itself to virtualize itself. So going one by one, so what happens in full virtualization is the operating system running inside the virtual machine is not aware that it is being virtualized. So you don't change any operating system code inside the operating system of the guest of the virtual machine. You only change you do all the translation inside the hypervisor layer. For example, if this hypervisor is running the Mac OS or the Windows OS or some OS, those OS are not modified. They just execute instruction as if they have the full access to the hardware, and inside the hypervisor you do all this translation. So this is called full virtualization, because the operating system is not aware that it's been virtualized, and all those instructions which is not available to be executed on the hardware is dynamically translated to the format which is understood by the hardware. So it's called dynamic translation, dynamic binary translation. So all these functions are done by the hypervisor itself. But as you see that would be more complex to implement and costly as well. That's why the second generation of virtualization is called para-virtualization, where the guest operating system running inside the virtual machine, that code is modified itself so that that guest OS knows that it is being virtualized and it has to do this dynamic translation inside the operating system itself. That's why you see this color here. So now they work in cooperation. They are more cooperation virtualization as compared to this one where they are fully unaware. And then we go to the third one where instead of changing the operating system, what they did is they changed the hardware on the motherboard. So then instead of making the software, the operating system inside the virtual machine that it is virtualized, they actually did some changes on the motherboard, on the chipset, so that it knows that it's going to run in a virtualized environment, and then this hardware runs in collaboration with the hypervisor in terms of meeting those machine instruction which is not supported across different operating systems. So there are three ways to do it. We'll go in more detail after this slide. First is full virtualization, where you don't change anything inside the virtual machine guest OS. Then it's a para-virtualization, where the OS inside the virtual machine and the hypervisor run in collaboration, and the OS is aware that it has been virtualized. So, and then there is the hardware-assisted virtualization, in which doing full dynamic translation inside the hypervisor it does on the hardware itself. So this is like full virtualization done, in which the dynamic translation is done on the hardware. Here it's in the software. That's how the full virtualization and hardware-assisted virtualization differs from each other. And a type 1 and type 2 hypervisor can be implemented is one of these three ways. Depends on what kind of virtualization you want to support. And different companies, they implement different way to virtualize. So for example, VMware and Microsoft, they support full virtualization, as well as they support para-virtualization, as well as they support hardware-assisted virtualization. And of course, each of them has different pricing, different performance footprint, different security requirements. So it depends on that. And again, you can only figure out which virtualization is best for you based on your benchmarking experiments. Right. So coming back to full virtualization, so as I said, this dynamic translation happens inside the hypervisor. So if you get some instructions from your higher level operating system which is not supported by the underlying hardware, what it does is it does emulation of that hardware or convert those instructions to the format which can be executed on that hardware. And the two popular open source emulator that is used in the full virtualization, they are called QEME and Bosch. So they are the two techniques adapted by these hypervisors. And of course, while the hypervisor is doing all those things, the operating system inside the virtual machine is not aware of all this dynamic translation, and it is sending instructions the way it sees it requires. And the second one is para-virtualization. So as I said, both type 1 and type 2 hypervisors can be para-virtualized. And what happens in that one is, in para-virtualization is, the OS, the operating system kernel, is aware that it is running on a virtualized infrastructure. And so what it does the dynamic translation inside the OS itself based on which hardware it is working. So the time when you install a virtual machine on that hypervisor, you pass this information to the virtual machine that what kind of hardware is available to you and what kind of translation you want to do. So based on that, you will have those kind of DLL or kernel files available inside the guest OS so that you can do that translation yourself. So the communication between the guest OS and the hypervisor layer is happens something called the hypercall. So this is just a terminology. It's hypercall. So hypercall is the way they raise interrupts to pass instruction to the underlying hardware. And then last one is you can also do full virtualization by not changing anything inside the operating system, but you actually change the chipset of your hardware so that it can dynamically translate the instruction from the upper layer hypervisor operating system to something that you can execute there. And those instructions normally would be around a memory hierarchy, either 32-bit or 64-bit, will be around the accumulator and other chips that you have on the motherboard. So all those things are done inside the hardware. And the two hardware that support this hardware system virtualization that include Xeon from Intel and AMD virtualization called Opteron. So as you see that to really work in the cloud computing discipline is not that easy. You need to understand, of course, first of all, what application you have. Then you understand on what kind of virtualization it's going to run, and then understand how your performance is going to be, and then also has a hit on your security. So you have to understand so many things in order to be able to a user or an engineer who can run and deploy and manage your application on cloud in a very elegant, efficient way. Because if you don't understand those, for example, if your application update is really slow and you debug your application logic, there is no bug in that. But then you want to realize why it is slow. So unless you know what kind of hypervisor you are using, what kind of translation they are doing, you cannot actually determine why it is slow. So for that, to understand that, you need to understand which is the best hypervisor to run your application, and then how does it impact in terms of your application runtime. So those details you can only know by knowing the specific of hypervisor environment. Either they're doing full virtualization, para-virtualization, or hardware system virtualization. Based on that, decide which is the best environment to run my application. So you need to know all those details. It's not just starting a VM inside the Amazon cloud and just hope that everything will run fine.